Okay then, so to continue from point 4, which is starting to plot the graph, what we should now have, and personally just a bit of advice for me, it's not necessary for your lab DAO to do this, but I think it makes life easier, is if in a table somewhere you just make yourself up a little, you've got the run numbers, if you like, down the side. If you just put your calculated values of R, effectively your mean R, with, unit, and your length, because these are the two things you're going to plot next to each other. It's literally a repetition of a column you might have somewhere else, but it just is a little bit easier if you've then got numbers in what you're going to plot on the graph if they're just written next to each other, and you're not kind of having to go back and look in two different tables to get your resistance from there and your length from somewhere else. Again, tip from me, I think that works really well, entirely up to you. But what you're going to do, you're going to plot a graph. There's loads of advice on plotting graphs. Again, you should study that independently. So what we're looking at on this one is resistance here. I'm looking, just to start with R on the y-axis and omega, and I'm looking for length and meters. And if you're going to put meters, it needs to be in meters. It's not enough just to say it. You need to actually have converted this at some point. Your crosses then need to be little points. Okay, little tiny sharp pencil. Do not do these in pen. Do not do this on a computer. Right, you will lose credit if this isn't done by hand. So there's graph paper available elsewhere on here. You can just download that, or you can download it yourself and print it off, or you can buy pads of graph paper. But it needs to be a little sharp pencil. Mechanical pencil's genuinely your friend for doing this. Every bit of raw data needs to be plotted, so you are plotting mean R. Alright? I know we technically haven't got a mean R, we had a mean V, but we used mean V and mean I to calculate R, so it is our mean value of R. I don't want your 3 repeat readings. Do not plot repeats. Okay? The x-axis, the y-axis and the x-axis don't have to start at 0. You can condense them down, but I think for this one, depending on what lengths you've chosen, it's probably going to come from about 0 anyway. But notice how mine, it's actually not going to hit 0, 0. That's fine. I mean, it's not. It shows there's an error in the experiment, but errors in experiments happen. That's what you're here to deal with. So these little x's need to be about the size of a tiny little 2x2 mil square or smaller. Not done in a felt tip pen. Nothing is done in pen on this. All this is in pencil. It needs to be big. Alright? So if your bit of A4 paper that your graph is on is there, and the actual graph area within it is there, your graph needs to be taking up minimum of half that. So if it's in the top half, okay, it's still not great though. Choose a better scale, try a different orientation. You want to make the graph as big as possible. If you make it small, you lose precision. And you're trying to use your graph to work something out. You don't want to be losing precision. Okay, other little minor points. There's more to go on the graph in a minute, but we'll get to those in a sec. So you want to mirror the level of precision on the way that you do your scales. So, for example, you wouldn't put 0.1. If it's to 3 sig figs, you'd put 0.100. 0.200, and so on. You're mirroring the level of precision to which this has been plotted based on the precision that the data was collected to. So mirror that in your scales. Likewise, if your resistances, were all done to 3 significant figures, you might put 10.0, 20.0, 30.0, or whatever your range needs to be. And you need to think a little bit about what your range is. If you get to it and you realise you've not made your scale big enough and your last point won't fit on the graph, sorry, you've got to plot it again. If you've collected the data, it needs to appear on the graph. What about if you've got something which, when you plot all your data together, in actual fact, let's say you ended up with this is your plot, and you've got points, just very roughly, which are sort of alright, which are sort of okay, but they're a bit flat, and the only way you can do that is because you've got one anomalous reading that's up here. Well, ideally you'd have spotted the anomalous reading when you did the experiment and maybe redone it, But what you should still do, I'm sorry, but you have to plot that graph. But that graph's not much use. So what you then do is you plot a second graph where you eliminate that and you plot the data. And then that's the one that you do your analysis based on. But you need to include the previous graph, otherwise you've just omitted data and tried to cover it up. And in a world where you're going to lose your job for tearing a page out, ignoring data does not go down well either. So for that, you'd do two graphs. You wouldn't need to worry about the first graph particularly, and you wouldn't need to do anything with it. You wouldn't even necessarily need a line of best fit on it particularly, or to calculate any gradients from it or anything like that. But it needs to be there. And then you need to have put a note in somewhere to say why there is this second graph and why it is that you haven't used it and you've omitted that data. Okay, so only other little thing about the sort of basic mechanics of a graph that I want to mention before we move on is sensible scales. I've seen all sorts of stuff. And I know it's a bit in, people do things in desperation sometimes because picking one scale makes the graph, you know, half the size of the graph paper. Basically, if your graph is less than half the size of the space you've got to put it in, you can double that scale and it will still fit. If it's half the size, that's the minimum, but then it's okay, it's half the size. But if it's any less than that, you can double the scale and it'll fit. Don't please go up in odd units or odd scales. So no like 0, 0.3, 0.6, 0.9, no, please don't do that. Basically, if you can't find 7.5 on your scale, it's not a good scale. Simple as that. Without, you know, yes, you're all good mathematicians, I would hope that you would, even on that scale, be able to find 7.5. But if you have to start working things out on a calculator to figure out how far along 7.5 needs to be, it's not a good scale. You can go up in 1s, 2s, 4s actually aren't great, but you can figure out 4s. If you go up in sort of 0.4, 0.8, let's say that's 5 squares. Every square is 1.25. It's 1 1/4. It's not a brilliant scale, but you can figure it out. 5s, and then obviously multiples, so you can go up in 10s or 0.1s or whatever. They are good scales. Don't use anything else. Right, so then your points are plotted. So what we've then got to do is get to the bit where we can get a gradient, because the gradient is what we're going to use. So this is where you need a line of best fit. Alright, you need a ruler. I can't really do this very easily, I'm afraid, and partly because I'm working with Mac, so I don't even have a straight line function I can use. So I'm doing this freehand. If you draw yours freehand, this is the point where I'll probably just give up marking it. Alright? Use a ruler. Right, rules for this. It goes through the points. Okay? It goes through the points, and it does not have to touch every point. It goes through all the points as a group as best as you can. It does not go through the origin unless it happens to go through the origin. Okay, if you're, we go a little bit deeper. If your points are here, then your line goes about there. It does not go like that. Don't do that, because that's ignoring all of your data. What was the point of doing the experiment? Likewise, if your line of best fit, all it does is join the first and last point. I don't know where this one comes from, but loads of people do this. So let's say you've got a little bit of scatter, and this is an extreme version, but this is to show you why it doesn't work. If you just join your first and last point together, what was the point of collecting any of that other data? Alright, it goes through the middle of the points. If it doesn't touch a single point, that's okay. It's a trend line. It's meant to follow the trend of where your points are. The more scatter there is, the more variability in the position of it, but it's meant to follow the trend. That's what it's for. So use a ruler for your line of best fit. It goes to the middle of your points. And if it happens to come back and go through 0, 0, then fine. But to be honest, it's more useful if it doesn't, because a little bit more advanced techniques later on, but you can use how far out it is from the 0, 0, from your origin, to do a bit of a calculation on how big your errors are, and you then correct your data for them as well. So it's a useful thing if it doesn't go through, because it tells you your error, and every experiment has error. We don't pretend that they don't. So don't force it to go through the origin, don't fit it to the first and last point, fit it to all of your points. Now, one thing I've not talked about yet is error bars, because I'm going to go back and do error bars in a little separate video. But if you have a lot of scatter, error bars can help. So this is a point where you might want to do things in a slightly different order and actually go back and do the processing of the errors up to the point where you plot a graph. because it can help with the line of best fit. So not to talk about where error bars come from just yet, because we'll get to that in a minute, but let's say that your error bars cover points that have got quite a bit of scatter. So something like this, and it's actually then very difficult to do a line of best fit that goes through them. Well, once you've got error bars on there, all you've got to try and do is get a line of best fit that touches every error bar if you can. That one, clearly, is a bit more than an outlier. That one's bordering on being an anomaly. It's sort of, I don't know, I wouldn't argue with you if you called it an anomaly or an outlier. I wouldn't. It's sort of on the borderline between the two. But that's maybe one I'd ignore. And honestly, that's a rubbish line of best fit. That's a bit too low at the beginning. I'm drawing these things freehand again. But error bars can help a little bit with this sometimes. But if you're getting quite good data out of it, then not a problem. Second minor issue some people come across is they know they're supposed to get a straight line, and they end up with something with a beautiful, neat curve in it. And it's clearly a curve as well. If you tried to fit a straight line to that, all you're doing is highlighting how wonderfully curved it is by putting a nice straight reference line next to it and going, oh yeah, look at that lovely curve. The thing is, you've got to do your analysis based on based on a straight line. There needs to be a straight line there. But if you fit a straight line to something which is clearly a curve, again, you're selecting and ignoring data. That's bad. So don't. Here's my bit of advice for you. From a student's point of view, when you're an actual physicist and an analyst, then you do more analytics, get a computer on there and get it to give you an equation, the curved line, and try and figure out what was going on. We're not expecting that from you. But just to prove that you do understand how lines of best fit work, then you put yourself a nice smooth curve on it, goes through the middle of the points, follows the same rules, should be as many points above as there is below. But with a bit of blurb, say, but I need a straight line as the analysis, so I'm either going to just take the first points, which is straight, and just base your analysis on these bits. Again, you're selecting data, but you've already got a problem, so at this point you've got to figure out how to deal with it. Or fit a straight line that does go straight through. You're covered then. You can do all the processing afterwards from the gradient, that's what we want you to do, and that's what you're getting marked on, but you've not ignored the fact that it's a curve. If you are getting a really serious curve, though, just go back, check all your processing, make sure you've not made a mistake somewhere. More often than not, you should be plotting something squared or something like that, and you've not done. For this, you're not plotting anything squared, but still it's a good opportunity to go and just double check all your calculations. But sometimes a curve is the result of the fact that you've got some error which is having a bigger and bigger and bigger effect on your data as it goes. So for example, if the current was changing, that could be changing the temperature, and that in turn could be having a knock-on effect on the resistance, and therefore the apparent resistivity of the material. So again, something which curves tells you there's something else going on, and given more time you would go and investigate. Okay, so from that you should be able to get your graph plotted. Then we'll look at what you do with it afterwards.